Okay, we're moving on now to topic 2 of chapter 4, and it's systems of linear equations, and we're introducing the augmented matrix. Now, if you were to read the textbook, it says that as we do systems of linear equations with 2 variables and further chapters that I don't think do 3 variables and 4 variables, it gets quite complex. And often they don't expect you students to do them by hand. So we would use a graphing calculator, and they mention that right in the book. So if you have TI-83s and those types of calculators, there's usually a function on there that illustrates matrix, and I will show it to you on this camera as well, on this calculator. But right now we're going to give you a little bit of a primer on what a matrix is. Well, a matrix, by definition, is simply an array of letters, numbers, that are set up in some form of chart where we have brackets around them. So this is a matrix, this is a matrix. These are all matrices. That's the plural. Now, we name a matrix by the way they're sort of listed or displayed. And each item in a matrix is called an element. So these are elements of a matrix. And then when we line them up in rows that are horizontal and columns that are vertical. We use the row and column to identify the kind of matrix that we have. So for instance, if this is our row and this is our column, this would be an M by N matrix. And so in this case, what kind of matrix would this be? Well, notice there are 3 elements and 3 elements. This is 1 row, 2 rows, 3 columns. So this is called a 2 by 3 matrix. And this is the one we're going to be using a lot in further calculations and what we've used a lot in previous things. So we talk about size and dimension. Again, it's depending on the position of the elements in rows and columns. So what type of matrix would this be? Well, how many rows does it have? 4. How many columns? 3. So this is a 4 by 3 matrix. And again, you have to say the row first, then the column. Now, there are some special types of matrices. Here, this is a square matrix of the order n, because notice there are 3 rows and 3 columns. So this is a 3 by 3 matrix. And square. In some cases you can have a single column. So there are 4 rows but 1 column. So this is a 4 by 1 matrix. Another name for this is a column matrix. And this one, what do you think this one's called? a row matrix. And it's one row, 4 columns, a 1 by 4. A few more items about the terminology of a matrix, and that is, first of all, where did this matrix come from? What might it have looked like before it was in a matrix? And again, this ties in with section 4.1. Well, this system of linear equations in 2 variables, if we were to put this would be called standard algebraic form. And if we converted this set of linear equations into a matrix, we would take the numerical coefficient of the x, which is a 1, the numerical coefficient of the y, which is a -4, and then our constant, which is 5. And then numerical coefficient of the x here, which is 7. There is no y term, so we put a 0 as a space filler, and our constant over here is 2. So this would be the standard form of linear equation in 2 variables. This would be its matrix equivalent. A couple of other things. Now, when we are identifying terms in a matrix, we think of what row they're in. Remember, the row comes first. So the position of this 1 is in its first row, first column. So 1, 1. This 4, it's in the first row, second column. First row, third column. And by the way, we don't say A11. We say A sub 1, 1. So think of these as like little commas separating them. It's not 21, because this is row 2 now, first column, row 2, second column, row 2, third column. Now, another term that's introduced here as well is called the major diagonal. If we had something like this, which is a 3 by 3, our major diagonal would be this term, and this term. And this would be A, first row, first column. This is A, second row, second column. This is A, third row, third column. So this would make up the major diagonal. Now, for some of you, you may know what I'm talking about already, because when we use our calculator, and I'll be showing you this a little later, we actually get to see how the major diagonal gives us answers to the solving of these systems of linear equations through the use of the augmented matrix. So I'm a little excited, but you needed to have this background, and that'll be your first quiz me on knowing what this is all about. And I didn't put the page reference, but we're now on page 184, and they are introducing how to convert from a standard form of the linear systems of linear equations in standard form to a matrix. So the key is it must be in standard form. That's the way you have to put it in the matrix. Sometimes They won't have it in standard form. You need to put it in standard form. And remember, that's ax plus by equals c. Now, if one of the terms are missing, you just put a 0 there. So here's our equation 1. There's our equation 2. Now, I can put a little dotted line here for a moment, and you'll see why. So if we take the coefficients of our first equation, a 2 and a negative 3, put that there. A 1 and a 2, put that there. This is called the coefficient matrix. Then if we put the 5 and the negative 3, that would be called the constant matrix. Now if you combine the 2 and 1, there's where you get the augmented matrix. And sometimes you see the augmented matrix illustrated in this particular form. Now I'm going to take time to show you on a TI-83. In fact, what I think I'll do is I'll move the camera in a little closer to show you this. What we're going to look at right now is how to convert standard form of two equations, systems of linear equations, into the matrix. Now there may be some repetition, but I think that's good. What we are interested in particularly when we convert from standard form into a matrix are the numerical coefficients. So when there's only a letter, there's a 1 as its coefficient. If there's no letter, then it would go into the matrix as a 0. So here we have a 2, a negative 3. Now if it's positive, we don't write the sign. But when it's negative, we must. And then a 5. And then here's our 1. Again, there wasn't a 1 there, but in reality there is, or something like that. We put the 1, the 2, and the negative 3. Now, in some textbooks, they use a solid line here. We're using a dotted line to separate the letters from the constants. So that would be the official augmented matrix form of this set of linear equations. Keeping in mind, by the way, that this x sub 2 is sometimes referred to as a y, because it was x and y. They're just saying two different letters. Now, another thing I want to go over is the identification of these, because you will be asked to identify them. Here I have by the number 2 a 1, 1. Now what does that 1, 1 refer to? Well, the first one refers to the first row. Remember, it's always row and column. And the second one refers to the column. So this is first row, first column. First row, second column. Now, here they're also changing. When you get to the constant column, they're using the letter K for constant. So this is the constant column, or constant row, and it's 1. And then we go to row 2. Well, the 1 is the first term in the second row, first column, second row, second column. and then constant second row. Now in some calculators, when you're putting in information, I know the Casio does this, when you're putting in the matrix into a calculator, they will ask you for A sub 1. Well, A sub 1 would be this first term. B sub 1, the second term, and then the constant C sub 1, the third term. Then it would take you to the second row, A sub 2, B sub 2, C sub 2. So you will be asked to identify, and again, if it's just a matrix without a constant column, then this one, in a sense, would be first row, third column. And another important thing is we do not read this number as an 11. That's not the proper way to read it. When you're identifying position in matrix, it's the first number is the row, the second number is the column. So this would be read 1, 1. Okay? A couple of little things, and again, there is a section on the Quiz Me where you'll be challenged on these, and again, my strong advice, do the practice so that you're prepared for the Quiz Me's. Now, what I'm doing relates to page 185, but it's actually some work I got from the practice. And I thought that might be a useful item. We're going to perform row operations. And just to give you a little practice as to what it's like. So here it's row 1 and row 2. This sign means the rows are switched around. And that's topic A over here. 2 rows are interchanged. So what will this look like? Well, we're going to take row 1 and put it where row 2 would be. And then row 2 goes where row 1 was. Okay, and if you put that into your practice or Quiz Me, that's the answer. So once again, this symbol is to interchange rows. So we're taking this matrix, performing this operation, and then it looks like this. All right, for example 2, there's your matrix. And some of this is intuitive that you can figure out yourself. And that is the second principle here. It says a row is multiplied by a non-zero constant. And then we do what is described. Well, here our non-zero constant is a 4. And it says we're going to take a 4, multiply it by each term in row 2, and then replace that as row 2. So notice we're not doing anything with row 1. So let's just write row 1 there. But we are replacing row 2 with something. So it says a positive 4 times the first term. So 4 times 4 is 16. 4 times a negative 6 is a negative 24. And 4 times a negative 8 is a negative 32. So we have carried out this row operation where we've taken a constant multiply it by each term in row 2, and replaced then row 2. In example 3, again, we're continuing with row operations. Here we want to take the constant, a -3, multiply it by row 1, and replace it as row 1. So we'll notice that row 2 doesn't change at all, so we can just write that here. So now we're going to take a -3 and multiply it by each term in row 1. So -3 times 1 is a -3. A -3 times a -3 is a +9. And a -3 times 2 is a -6. So we have made those row modifications following this charge of our row operation. Constant times row 1, yielding and replacing row 1. Row 2 doesn't change at all. Now, in number 4, it starts to get a little more complicated. Let's look at what our instructions are. Well, they want us to multiply row 2 by this constant 7. So multiplying row 2 by the constant 7. Then we're going to add that to our row 1 item, and then replace row 1 with this. Now notice, in this case, row 2 again doesn't change. So we could just write row 2 in. Row 2 is not changing. So we now go 7 times 1 is 7. Let's try that one again here, because I'm going by row 2. 7 times 4 is 28. 7 times 4 is 28. Then we're going to add it to row 1. 28 plus 1, 29, and that's what we replace. So this now becomes 29. All right, 7 times a -6 is a -42. 7 times a -6 is a -42. Add it to row 1. A -42 and a -3 gives me a -45. So again, 7 times our second term in row 2, a -6 gives me a -42, and a -3 gives me a -45. 7 times a -8 gives me a -56. A -56 plus 2 is a -54. And we have successfully then carried out this row operation. Multiplying a constant by each term in row 2, adding it to its corresponding value in row 1, and then replacing row 1 with our results. In number 5, the row operations we're asked to do is to take a constant, multiply that constant to the items in row 1, add it to row 2, and then replace row 2. So, in this case, row 1 remains unchanged, so we can just put row 1 there. And while we're at it, here are instructions. Row 1, we're going to multiply it by this constant, add it to row 2, and then replace it in row 2. So again, row 1 stays the same. And now let's do the instructions. So our constant is 5. We're going to multiply it by each term in row 1. So 5 times 1 is 5. Add it to row 2. That makes that a 9. And then replace it in row 2. 5 times a negative 3 is negative 15. And a negative 6. Make that a negative 21. And then 5 times a negative 8 is a negative 40. Well, let's try the right row here. You got to be careful. Let's do it again. 5 times, in this case, a 2. 5 times 2 is 10. Add it to a negative 8. That gives me a 2. And I believe, I should check my work, that is correct. In example 6, it's basically the same form, except our constant now is a 2. So 2 times 2 times 1 is 2. Add it to 4, gives you a 6, and replace row 2. 2 times a negative 6, 2 times negative 3 is negative 6. I'm thinking ahead. And negative 6 gives me my negative 12. And then 2 times 2 is 4. 4, a positive 4 and a negative 8 gives me my negative 4. And again, part of it is becoming acquainted with what you have to do. And if you can read your lines, and we've been using row C in a sense, a constant. The multiple of one row is added to another row. And it depends on your letters. This next example, instead of doing a row operation, they want you to identify the row operation. So they're giving you 2 augmented matrices, and they want you to study it and see what was done to it. Well, as we look at row 2, row 2 is unchanged. So we look at row 1. Row 1 is different. So I've taken the liberty of saying that something is going to happen to row 1, this row 1, and then it's going to be replaced over there. Now, we just have to look at what was the constant that was there that became our new row 1. So here we had 3 becomes a 1, 12 becomes a 4, and a negative 12 becomes a negative 4. So what was done, in a sense, to this row to make it that row? I'm sure you're thinking, and you're saying, oh, I know. They multiplied every term in this row by what? What was the constant they used to get this? And the answer is 1/3. So if you take 1/3 of each item in row 1 and then replace it, you get this new matrix there. And that was what was done. Looking at this one, it's set up just a little differently. In the other, they use this sign. Here they're saying this is matrix A, this is matrix B. What happened to these matrices? In a sense, what was the row operation that was done to result in this? Now we notice row 1 stays the same. And row 2 has changed. So you kind of, you're brainstorming, wondering what went on. Well, could they have done something to row 1, added it to row 2, and then replaced row 2? And in fact, that's what it was. Now, they may not give you this right away, so you need to, you're brainstorming. This is a puzzle, and you're checking it out. So, and again, I did these just the other night, so I have a little fresh memory of my thought process. So here we have a -1, and then here we have a 6. So what do we need to do to a -1 and then add it to a 6 to make it 0? Well, we have to multiply it by something. And if you said we're going to multiply it by 6, that's a good start. And again, you might have to change this if it doesn't work. But watch it now. -1 times 6 is a -6. A -6 and a +6, adding it to row 2, replacing it, becomes a 0. Let's try it on the second one. 6 times 2 is 12. Added to a -2 makes it a 10. Replace it in row 2. Yeah, that checks out. 6 times a -3 is a -18. Added to the 2 is a -20. This is the operation that was done to this matrix to make it this one. Now you're going to have some on your practice and then quiz me. And again, do the quiz me, well, practice first, because then often the quiz me is very similar, and take some notes and then study. As we do this particular example, and they're asking us to solve it using matrix. And I believe we're probably on another page now. 586 or so. First, let's change this from its standard form into a matrix. So the constant 3, -5, and a -4, a -6, a -10, and an 8. Now, let me just mention, when you see something like this, I don't know if you spotted anything fishy or tricky, but notice here, 3, 6, 5, 10, 4, 8. What we were just working on, if you multiply each of these by a 2, in fact, let's just do that. I'm going to multiply this by a 2 and get a 6. This is a negative 10, and this is a negative 8. And hopefully I copied that down correctly. Let me double check it. One little sign will mess you up. Now this is positive, so this is positive. So again, I'm going to multiply this row by a 2. I get that. And now notice this row. And we're tying this into what we did in 4.1 as well. Notice if we were to add these rows together, we end up with a 0, a 0, and a 0. Now I want to review this as well. When you did what we did in section 4.1 and you add them up, and you end up with 0 equals 0, which is a true statement, this is a case in which actually these equations are the same, so they are an infinite number of solutions. Because as you plot one line, the other line is right on top. So every solution for one set is a solution for the other. And there's an infinite number of solutions. And it's sometimes shown this way. You don't get what we call a major diagonal that I'll be showing you a little later. Okay, so how in fact do we write this into the quiz me in your test? There is a special form. All right, this is example 1. It's in the textbook on this page. So we did a number of other things to go over background items. And now they're asking us to solve this using matrix. So step 1 is to convert this into a matrix. We're just going to take the constants here. Already have that. So as we look at this, we want to actually eliminate one of these columns, and if you were to go through all of the steps in the textbook, we would not have enough room. So I'm going to kind of condense it and maybe give you a little insight into what might be done. For instance, if we wanted to get rid of this column, what would we multiply this column or this row by? Think about it. And this goes back to section 4.1. And the answer would be a 2. And then what would we get? Well, we would get 3, 4, 1. But now this would be a 2. This would be a negative 4. And this would be a 14. Now, again, this is a little system I use, and it may be useful to you. Otherwise, you can follow that long system in the textbook. And what happens now? Well, I'm going to put that line, and I'm going to get 5, and I'm going to get 15. Now remember, this is 5x equals 15, because now this column adds out. And now we're going to divide both sides by 5, and I get x equals 3. Wow, that was pretty short. So if x equals 3, and we could use either one of these, let's say this one right here, if x is 3, this is going to be 2 times x sub 2 equals 7. Now we're going to transpose this. This becomes a negative 3, so I get 2 x sub 2 equals 4. Divide both sides by a negative 2. I get x equals a negative 2. So my ordered pair would be 3, comma, no, well, that's my first x, because this is actually my y here, so that would be a negative 2. I noticed in one of my other videos that I had the negative down here, but then when I put it up there, that was one of the little errors that I spotted. Okay. Something I should add to this, that if you're using your TI-83s, the display matrix of the answer looks like this, where we say our major diagonal are 1s, while these others are 2. And this is interpreted as 1x equals 3. And then this would be a 0, but this would be x sub 2, or our y, as it used to be, equals a negative 2, which is what we got. And in the textbook, they speak of this display when you do your matrix, that again, you have 1s in the major diagonal, and then m then would be your x sub 1, and your n is your x sub 2. Again, it's a little confusing that they've gone from x and y to x sub 1, x sub 2, but again, sometimes the letters are A and B, C and D, E and H. So again, generically I think it's probably okay to do it, and that's what they're doing. All right, we have one other that we need to do.